As the rest of class gets in here, we're going to get started. First thing before we do get into the actual lesson is just I want to talk about the last few weeks of school here, what we're going to be covering, what that is going to be this week. Oh, but first, good morning, welcome back. It's nice to see you guys. Nice to have people in my classroom. It's going to feel really weird next year when they have like full classes. So yeah, this week we're going to be covering chapter 3 from the textbook, dealing with like scatterplots and linear regression, least squares regression lines. If you know what those are, awesome. If you are hearing it for the first time, that's totally fine as well. That's awesome. We'll talk about it this week. We'll see some examples. We will not be doing an activity for this because I just want to kind of get through all of the things that are in chapter 3 this week. So for you guys today and tomorrow. I will have like a study guide as I normally do for the chapters and some practice problems available for this chapter in Canvas. I have not got those ready quite yet. But for the purposes of this class, we will be skipping chapter 12. All right. I will have resources for chapter 12 available in Canvas so you can look and see what's in it. But based on the time that we have and when the test is and all this stuff, the best recommendation I got from people who have taught this class before is skipping chapter 12 was the best option because it has the smallest probability of showing up on the exam out of all the different things that we cover. So we're going to skip it as far as our live sessions go so that we can do some review and some practice problems. Next week, we're going to look at the free response questions that have been released from this year's exam, from the exam that happened last week. So we'll get an opportunity to see what the type of questions that they are asking this year on the AP exam. So that will be hugely beneficial to us to kind of go over those questions. Not that you'll get the same questions on your exam, but it gives us an idea of what's going to be on the exam. So we'll go over those, look at how to solve those, look at other examples and review over the next 2 weeks after this week, and then school will be over. That'll be it. We got 3 weeks left, including this week. All right. So this is our final push. I think that's about all I wanted to say about that. All right, so we're going to get started with our lesson on chapter 3 today. We're going to cover 3.1 and part of 3.2 today. We'll finish up 3.2 tomorrow. There's only 2 sections in chapter 3, and then we'll look at examples to hopefully make this make sense. So, where is it? That's the one I want. There we go. Yeah, that works. And that one. Perfect. All right, so here we go. Chapter 3 is describing relationships. We're going to be doing scatterplots and correlation. This is describing relationships specifically between 2 quantitative variables. All right. Chapter 11, we were dealing with categorical variables and describing the relationship between those using like 2-way tables, 1-way tables, right? This is now dealing back with quantitative variables. All right, our objectives today in this section, right? We need to be able to identify explanatory and response variables in situations where one variable helps to explain or influences the other. Make a scatterplot or display the relationships between 2 quantitative variables. Now, again, remember, if you're taking the AP exam, you're not going to be expected to draw or produce any graphs, scatterplots, dot plots, any of those things. You may need to have it pop up on your calculator so you can use it. Right? You might need to sketch one so you can use it to answer other questions, but you will not be able to submit those types of things. Right? So it's going to be important to be able to use your calculator to produce these because it'll be faster than drawing it. And we'll go over that as well. Right, describe the direction, form, and strength of relationship displayed in a scatterplot and identify outliers in a scatterplot. Interpret the correlation. understand the basic properties of correlation, including how the correlation is influenced by outliers. We need to use technology to calculate correlation. There's actually a variable that we use for correlation. It's called R. We'll see that today. And explain why association does not imply causation. We'll see an example of that, or I'll describe an example of that later. All right, so explanatory and response variables. Most statistical studies examine data on more than one variable. In many of these settings, the two variables play different roles. A response variable measures an outcome of a study. It's the thing that you're measuring. The explanatory variable may help explain or influence changes in a response variable. An explanatory variable could be a treatment, a specific thing, right? That can explain certain responses. Note, in many studies, the goal is to show that changes in one or more explanatory variables actually cause changes in a response variable. However, other explanatory response relationships don't involve direct causation. Would anyone like a moment to write down these definitions for their notes if you're taking notes? So we can display relationships with scatterplots. A scatterplot shows the relationship between two quantitative variables measured on the same individuals. The values of one variable appear on the horizontal axis, and the values of the other variable appear on the vertical axis. Each individual in the data appears as a point on the graph. It's kind of like doing a dot plot with two variables. In a traditional dot plot, it measures the outcomes of one variable. We stack up all of our points. In this case, we're using two variables as like two axes of a dot plot, and they create coordinates. All right, and when we make a scatter plot, we need to decide which variable should go on each axis. Remember, the explanatory variable goes on the x-axis. Explanatory x-axis. Which means the response variable goes on the y-axis. We need to then label and scale your axes. Make sure you have clearly labeled when you're creating your own scatter plot what each axis represents, and then scale those appropriately. In any graph that you make, remember that the distance between each number, between each hash mark on your graph must represent the same distance for each one. You can't go from 0 to 5, then 5 to 20, then 20 to 25 in your scale. It should be a 5, 10, 15, 20. It needs to be uniform. That goes for x-axis and y-axis. You do not need the same scale for both axes, but they must be consistent on each individual. And then once you have your axes all ready, you plot your points. Would anyone like a moment to write anything down from this screen? All right, to describe a scatterplot, follow the basic strategy of data analysis from chapters 1 and 2. Look for patterns and important departures from those patterns. As in any graph of data, look for the overall pattern and for striking departures from that pattern. You can describe the overall pattern of a scatterplot by the direction, form, and strength of the relationship. An important kind of departure is an outlier, which hopefully we're familiar with at this point, an individual value that falls outside the overall pattern of the relationship. Two variables have a positive association when above average values of one tend to accompany above average values of the other, and when below average values also tend to occur together. Two variables have a negative association when above average values of one tend to accompany below average values of the other. Here we have an example scatterplot comparing percent of the population taking an SAT and the mean math score. Describing the scatter plot, we have there is a moderately strong negative curved relationship between the percent of students in a state who take the SAT and the mean SAT math score. Further, there are two distinct clusters of states and two possible outliers that fall outside the overall pattern. All right, and so again, this is negative because as we're going from left to right, we're going down. It's kind of like a negative slope. It goes down from left to right. And it's curved because as we go, it kind of goes fast here, slows down, and kind of follows a curve. All right. And we see our distinct clusters here. We've got an outlier here and possibly an outlier over here. Okay. So this is how we can describe scatter plot. All right, the strength, moderately strong, direction, negative, form, curved. We could have linear, right, if these are more straight in their pattern, right? But in this case, it is curved. Anyone like a moment to write anything down from the screen? Are there any questions? Anything to clarify? We have another scatter plot here. This is from an example in the textbook comparing points per game and wins among SEC football teams. So here we have our description here. Direction. In general, it appears that teams that score more points per game have more wins, and teams that score fewer points per game have fewer wins. We say that there is a positive association between points per game and wins. And that's because as we go left to right, we're increasing. It's positive. Higher values go with higher values. Lower values go with lower values. Form. There seems to be a linear pattern to this graph. That is, the overall pattern follows a straight line. This is obviously, compared to the previous example, this is much more of a straight pattern, a linear pattern, than the curved pattern we saw in the other one. And strength. Because the points do not vary much from the linear pattern, the relationship is fairly strong. There do not appear to be any values that depart from the linear pattern, so there are no outliers. We could, like, if you guys recall from previous math classes, when we have a scatter plot, we can draw a line of best fit that we think could fit the pattern for these data points. That line would be pretty straight, and a lot of these points would be relatively close to that point. Is there anything I can clarify here? All right, so we can measure our linear association using what's called correlation. A scatterplot displays the strength, direction, and form of the relationship between two quantitative variables. That's what we previously saw. Linear relationships are important because a straight line is a simple pattern that is quite common. Unfortunately, our eyes are not good judges of how strong a linear relationship is. The correlation R. So we have this new kind of statistical variable here called R. Measures the direction and strength of the linear relationship between two quantitative variables. R is always a number between -1 and 1. When it is positive, this indicates a positive association, essentially a positive slope for the line. When R is negative, this indicates a negative association, negative slope to the line. Values of R near 0 indicate a very weak linear relationship. Think of a line with slope 0 as just a horizontal line, I believe. Yeah. Right. The strength of the linear relationship increases as R moves away from 0 towards -1 or 1. The extreme values of r equaling -1 and r equaling 1 occur only in the case of a perfect linear relationship. So chances are you're never going to actually get an r equaling -1 and r equaling 1. You'll just get really close. Would anyone like a moment to write anything down from this screen? So here's some examples of different scatter plots that have different correlations. Right, we see the first one here, correlation is r equaling 0. There's no obvious pattern. It doesn't look like necessarily there's just no obvious pattern. Essentially, the line of best fit will be a horizontal line through the middle of all the points. Right, the next one we have r equaling -0.3. We have a slight negative slope to a line of best fit. 0.5, we have like a nice positive slope. -0.7, again, negative slope. 0.9, this is a really good, strong correlation here. The points are closer together and look linear. Then we have -0.99. This is, again, is a strong negative correlation. Points are very close together and very linear. Right. So kind of the less scattered the points are, closer together they got, the correlation should get closer to -1 or 1. Calculating correlation. This is something that you're not going to want to do by hand. The formula for R is a bit complex. It helps us to see what correlation is, but in practice, you should use a calculator or software to find R. Suppose that we have data on variables x and y for n individuals. The values for the first individual are x1 and y1, kind of like coordinates. The values for the second individual are x1 and x2 and y2, and so on. The means and standard deviations of the two variables are x bar and s sub x for the x values, and y bar and s sub y for the y values. The correlation R between x and y is this big mess. All right, R equals 1 divided by n minus 1 times the product of the essentially standardized score of x times the standardized score of y, added them all up. This could lead to many, many, many calculations in your calculator, depending on how many data points you have. We can write this in less notation using this form here. R equals 1 over n minus 1 times the sum of the standardized scores for x and y, essentially. That's not technically what these are called. They don't have a specific name, but they look like what we do to standardize a score. And if we go back to just what z equals, right? And we're multiplying those bad boys together. It's a lot. Your calculator will do this for you. For example, there's several things we can do on the calculator that can get us these values. If you look here, I have an R value. This is using the linear regression t-test, which is technically part of chapter 12, but we don't need to look at chapter 12 to use this thing. It will find R for me and also some other values that come up in section 3.2. Essentially, all we have to do is put our data into the lists, the statistical list, L1, L2, L1 being your X explanatory variable values, L2 being your Y response variable values. And then if we calculate, wait, no, I don't want to do that yet. Go back to So we can calculate what's called the linear regression, which we'll see in a minute. We want this one. There's 3 different linear regression calculations in your calculator. We want the one that says a plus bx. It should default to x list L1, y list L2, frequency list, we don't care. It will find my line of best fit, essentially, which we go to vars, y vars function, and just tell it to store in y1 on your graphing calculator there, and then calculate. Okay. Again, this will give me my my R value, R squared, which is another value we'll see later, and the y-intercept and slope of that line, which again we'll see a use for in 3.2. But here's R, which is kind of the thing that we don't want to calculate by hand. So as long as we put in the lists, we can use the linear regression to find R. And that saves us time. We can also look at the scatter plot with the line of best fit going through it. All right, so that's my brief calculator interlude. Facts about correlation. How correlation behaves is more important than the details of the formula. Here are some important facts about R. Number 1, correlation makes no distinction between explanatory and response variables. Number 2, R does not change when we change the units of measurement for X, Y, or both. Essentially, if we transform these things, the correlation stays the same. Correlation R itself has no unit of measurement. It's just a value. Here's some cautions. Correlation requires that both variables be quantitative. Do not use this with a quantitative and a categorical variable. Correlation does not describe curved relationships between variables, no matter how strong the relationship is. Right, that would be a different type of regression if we wanted to do a curved fit, and that's not what we're doing. Correlation is not resistant. R is strongly affected by a few outlying observations. And this is because we use the mean when calculating R. And the mean is not resistant to outliers. Right? Outliers will cause things to go where they're not supposed to go. Does anyone need a moment to write anything down here? All right. So we're going to see a few examples of scatter plots here, and we'll just talk about what the possible R value is and what it could mean. Right, in this case, we have boats registered in Florida versus manatees killed by boats. All right, this looks fairly linear. Does not look curved really. It's not exact. Right, but we're looking at probably like R equals 0.8 or something like that, 0.9. It's pretty good. Points are fairly close together. In context, that means that it looks like typically the more boats that are registered in Florida, the more manatees that are killed by those boats. Right, we're just kind of relating how one could be related to the other. We have storms predicted versus storms observed. This is a little more scattered here. We have an outlier over here that's outside of the main cluster. Right. This most likely has a very low slope. Maybe like 0.2, 0.25 if we have to guess, right? So there is a very weak correlation between storms predicted and storms observed. We have healing rate of limb 1 versus healing rate of limb 2. In this case, it pretty much looks like there's no relationship between these things. Knowing that one limb healed at a certain rate doesn't really have any effect on the other limb. We can't say that if one heals fast, the other one heals fast. This is basically an R of like 0. It's really just spread out. And again, we have last year's percent return versus this year's percent return. If anything, this might have a slight negative R, maybe negative 0.1. Right? But again, they're very spread out. It's a weak association. All right. So that's the end of the presentation for section 3.1, essentially just dealing with scatterplots and correlation, seeing how we're relating these two quantitative variables together. Last thing I want to talk about is why association does not imply causation. We can find association between two quantitative variables where one is not necessarily causing anything about the other. My favorite example of this is popsicle sales versus shark attacks. Okay. More popsicle sales most likely associate with higher shark attacks, mostly because during the summer people buy more popsicles and more people go to the beach. So there will be more popsicle sales, and there is a possibility of having more shark attacks. The popsicle sales are not the cause of the shark attacks. Right? But there is probably a correlation. There would be an R of probably a positive slope, showing that there could be an association, but that is not the same as causation. People buying popsicles is not causing more shark attacks. Right? So that's my favorite example of association not implying causation. Okay. Are there any questions? Anything I can clarify? All right. So then I'm going to end that one. We're going to jump right into section 3.2 and get into some of this one. All right, so section 3.2 is about our least squares regression. This is where we actually get into our kind of line of best fit stuff dealing with scatter plots. All right, we need to be able to interpret the slope and y-intercept of a least squares regression line. Use the least squares regression line to predict y for a given x. Calculate and interpret residuals and their standard deviation. Explain the concept of least squares. Determine the equation of a least squares regression line using a variety of methods. Most likely you're just going to use your calculator for this. Construct and interpret residual plots to assess whether a linear model is appropriate. Again, you'll use your calculator to be able to do this. Assess how well the least squares regression line models the relationship between two variables and describe how slope, y-intercept, standard deviation of the residuals, and r-squared are influenced by outliers. That's again a big old chunk of stuff. We're going to get through some of it today, the rest tomorrow, and then we'll do examples. So first, we have a regression line. Hopefully, in previous math classes, you saw what a regression line is. We can call this the line of best fit. We use our calculator to determine this line. Right, the linear straight line relationships between two quantitative variables are common and easy to understand. A regression line summarizes the relationship between two variables, but only in settings where one of the variables helps explain or predict the other. A regression line is a line that describes how a response variable y changes as an explanatory variable x changes. We often use a regression line to predict the value of y for a given value of x. Again, we have an example here. This has to do with the value or price of I think they're doing Ford F-150 based on the number of miles it's been driven. A regression line is a model for the data, much like density curves. The equation of a regression line gives a compact mathematical description of what this model tells us about the relationship between the response variable y and the explanatory variable x. Suppose that y is a response variable plotted on the vertical axis and x is an explanatory variable plotted on the horizontal axis. A regression line relating y to x has an equation of the form y hat equals a plus bx, essentially standard form for the equation of a line. In this equation, y hat is the predicted value of the response variable for y for a given value of the explanatory variable x. B is the slope, the amount by which y is predicted to change when x increases by 1 unit. And A is the y-intercept, the predicted value of y when x equals 0. So all these parts do exactly as we would expect them to do based on what we know about linear equations and linear functions. Then we need a moment to write anything down about the regression line. So here we'll interpret slope. The regression line for our scatter plot here, miles driven versus price in dollars, is shown below. They've done price hat, which is the y hat, equals 38,257 minus 0.1629 times miles driven. Miles driven is our x variable, the explanatory variable. We want to identify the slope and y-intercept of the regression line and interpret each value in context. Right, the slope b equals negative 0.1629 tells us that the price of a used Ford F-150 is predicted to go down by $0.1629, 16.29 cents, for each additional mile that the truck has been driven. So we have a negative slope or a negative association. The y-intercept, A equals 38,257, is the predicted price of a Ford F-150 that has been driven 0 miles. Right? The value of B, right, this negative slope, is not the same as the correlation. Those are going to be different values. The correlation R tells us how close to a linear model the points are. The slope is the actual slope of the line. For each unit change in x, how much does y change? Right. Now, if you have a negative association, R is negative, your slope should also be negative. Right. If you have a positive association, you should have a positive slope. Is there anything I can clarify about that? Any questions? We can use a regression line to predict the response y hat for a specific value of the explanatory variable x. We can use the regression line to predict price for a Ford F-150 with 100,000 miles driven. Okay, we have our formula. Price hat equals 38,257 minus 0.1629 times miles driven. We have our little graph over here. We could trace up on the graph to the line and over to get an estimate. Or we can just plug it in the calculator. We'll replace miles driven with 100,000 and do the calculation. We get price hat is $21,967, which matches pretty closely to what we probably would have estimated, about 22,000, if we just use the graph. Right, so we can use this to make predictions. Right. The accuracy of the prediction depends on how much the data scatter about the line. While we can substitute any value of x into the equation of the regression line, we must exercise caution in making predictions outside the observed values of x, which means it's safer to limit yourself to making predictions that are within the range of the values of x from your sample data. Extrapolation is the use of a regression line to predict far outside the interval of values of the explanatory variable x used to obtain the line. Such predictions are often not accurate. Don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. That brings us to residuals. In most cases, no line will pass exactly through all the points in a scatterplot. A good regression line makes the vertical distances of the points from the line as small as possible. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. The residual is equal to the observed y minus the predicted y, which we can write as y minus y hat. And so, like, if we have this data point here, the vertical deviation from the line is this distance. The vertical distance here is the residual. Right? It's how far away this point is from the regression line. If your point is below the regression line, right, that residual will be negative. If it is above the line, you're going to have a positive residual. Different regression lines produce different residuals. The regression line we want is the one that minimizes the sum of the squared residuals. Squared residuals are used because they give us positive distance. Any number squared will be a positive number. The least squares regression line of y on x is the line that makes the sum of the squared residuals as small as possible. Essentially, it's the best line of best fit because it has the smallest residuals. And this is kind of a picture of squares. We want these squares to be small as possible. One of the first principles of data analysis is to look for an overall pattern and for striking departures from the pattern. A regression line describes the overall pattern of a linear relationship between two variables. We see departures from this pattern by looking at the residuals. A residual plot is a scatter plot of the residuals against the explanatory variable. Residual plots help us assess how well a regression line fits the data. So here we have our scatter plot for miles driven versus price. And here is the residual plot. So the line, the horizontal line here represents a residual of 0. So a point that lies right on the regression line would lie right on this line equaling 0. These points represent how far away each corresponding point is from the regression line. The more concentrated these points are to the line, the more accurate, right, our regression line is, and the more well it fits the data. A residual plot magnifies the deviations of the points from the line, making it easier to see unusual observations and patterns. The residual plot should show no obvious patterns. The residuals should be relatively small in size. So, for example, we have a residual that looks like this. Wrong buttons. Right. And its original scatter plot looked like this. It was curved. So a linear model doesn't fit for this data set because it's very obviously curved. Right? And this results in a very weird pattern that shows up on the residuals. To assess how well the line fits all the data, we need to consider the residuals for each observation, not just one. Using these residuals, we can estimate the typical prediction error when using the least squares regression line. Essentially, we're finding the standard deviation for the regression line. Just like we've done with single sets of data, we can find the standard deviation, which is the typical deviation from what we would expect. We're finding the typical deviation from what we would expect using the regression line. If we use the least squares regression line to predict the values of a response variable y from an explanatory variable x, the standard deviation of the residuals, s, is given by this formula, which is very similar to how we find standard deviation. It's just a slight difference. All right, so we have the square root of the sum of the residuals squared divided by n minus 2. And this is not n minus 1 because we're dealing with two data sets. So it ends up being n minus 2. And we have the square root of the sum of y1 or yi minus y hat squared divided by n minus 2. Again, this is the squared residuals. So we're adding up all the squared residuals divided by n minus 2, take square root of that thing. This value gives the approximate size of a typical prediction error or residual. Again, this value, I believe, will be found in your calculator if your data sets are in a list. And it's using this linear regression t-test, I believe, finds S. All right, and I've already found the regression equation, so I actually told my calculator that it's stored in y1, so it knows what equation to use. This gives a lot of values. We get S right here. So again, use your calculator to find S. You're not going to want to do this by hand. This would really suck to calculate. The standard deviation of the residuals gives a numerical estimate of the average size of our prediction errors. There is another numerical quantity that tells us how well the least squares regression line predicts values of the response y. The coefficient of determination r squared is the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. We can calculate r squared by using the formula 1 minus the sum of the residuals squared divided by the sum of y1 minus y hat, or y bar. So the residuals uses y hat, this is using y bar, so it's using the actual mean of your response variable squared. R squared, blah, blah, blah. Again, don't worry about the formula. Your calculator will find this value for you. Put it in the lists, use one of the two commands. I'll go over those things again tomorrow. R squared tells us how much better the least squares regression line does at predicting values of y than simply guessing the mean y for each value in the data set. In section 3.1, We looked at the relation between the average number of points scored per game, X, and number of wins, Y, for the 12 college football teams in the SEC. A scatter plot with the least squares regression line and a residual plot are shown. The equation of the least squares regression line is y hat equals negative 3.75 plus 0.437x. Also, s equals 1.24 and r squared is 0.88. This is the data set that I used in the calculator. Right, and so we can see where they have these values. Right, they have 1.24 for s. They've just rounded this to 2 decimal places. R squared, they did 0.88. Again, they rounded to 2 decimal places. Right, A, negative 3.75. B, the slope, 0.437. Right. So using the calculator, we'll get all the values for this that we need, as long as we've populated the lists correctly. Right. Your calculator will do all these calculations, give you all the needed values. So we're going to calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. The predicted amount of wins for South Carolina is, and this is where they use the y hat formula. Based on the number of points per game they scored, they should have had 9.4 wins. Residual, y minus y hat, which is their 11 wins minus the 9.4 expected wins, is 1.6 wins. South Carolina won 1.6 more games than expected, based on the number of points they scored per game. Right? So essentially, they did better than expected, right? And that's what our results here show. So that's how we are interpreting the residual, based on the context. Now, is a linear model appropriate for these data? Explain. Here's our residual plot. Because there is no obvious pattern left over in the residual plot, the linear model is appropriate. If we were to see an obvious pattern, like a curve, the linear model may not be appropriate. We're going to interpret the value s equaling 1.24. When using the least squares regression line with x equaling points per game to predict y, the number of wins, we will typically be off by about 1.24 wins. And our r squared value of 0.88, about 88% of the variation in wins is accounted for by the linear model, relating wins to points per game. Meaning, essentially, the linear model is a good representation. It's pretty darn close. All right. All right. And we're going to stop here. We'll cover the last part of this tomorrow. It gets into something else. All right. And stop that. All right. Okay. So that's what we're going to cover today. We'll get the last part of section 3.2 tomorrow, and then we'll look at more examples on how we're using this scatterplot correlation and least squares regression lines. And I'll show you. I'll definitely show you the different things you can do on the calculator with this, so that we're ready for that. But other than that, that's all we're going to cover today. If you have any other questions, comments, concerns, need help with stuff, please make sure you're letting me know so I can help. Have a great rest of your day, and I will see you all tomorrow.